Hello, everyone. So we are going to present Megatron-FSDP. I think there were already many talks about FSDP today, but we are going to share NVIDIA side of the story, how we optimized the performance of the fully sharded data parallelism. All right, so talk is going to go over a brief recap of FSDP. Already you guys are familiar with a lot of talks today, but we're going to do a short recap. And then we're going to talk about what Megatron-FSDP as an overview, and then go over many of the optimization we did to improve the performance of it to actually accelerate large language model training. And then finally, my co-presenter Cory today is going to talk about the API details. So this is a collaboration with many NVIDIA folks here, so I'm going to just have a brief moment to acknowledge their help. And then let me talk about what FSDP is. So the idea of FSDP is basically sharding the model state of the the model across the GPUs, and then the model states here basically include the parameters and the gradient, and then optimizer states. And depending on what precision you're going to use for the compute, there could be two copies of the parameters. So they basically look like this. And then compared to the baseline data parallel training that actually replicates all these model states across GPUs, FSDP basically keeps only a unique copy in each GPU, so keep the per GPU memory usage low. So this is a very important thing to actually train an extremely large deep learning model like a generative AI in a large-scale system. So how it works? So this whole model state sharding happens at the beginning of training. And then this sharded parameter is supposed to be unsharded, another word like gathered before computation in both forward and backward computation. And after the backward computation, the gradient computed is supposed to be resharded or reduced scattered to actually keep the per GPU memory usage low. And then the key of this FSDP to make it performant, all this computation is supposed to be hidden under computation, as shown in this diagram. So this happens by using two different streams, and then we basically co-allocate and then keep all this communication hidden under computation. So why people like FSDP? As you know, there are a lot of talks already. So it's much simpler compared to the complex 3D parallelism, which usually refers to tensor parallelism, pipeline parallelism, or extra. You can basically think about only one dimension to deploy your GPUs, your model to GPUs. And then secondly, it's more compatible than compared to the pipeline parallelism. So it can be used for hybrid model that has a different architecture in different transformer layer. And then also you could forget about the load balancing with the transformer layer, embedding, and then loss function. So it's much simpler. And then the question here is actually if it is performant. So this is a motivating data that I want to show here. So this is the result of Llama 3 4.5 billion training on 64 NVIDIA GB200 GPUs. So there are 3 bars, and the y-axis here indicates the teraflops per GPU. And then blue bar on the leftmost side is the 3D parallel training result using NeMo framework from NVIDIA, and it uses tensor parallel size 4, pipeline parallel size of 8, and context parallel size of 2, which is basically data parallel size 2 as well. But compared to that, our baseline FSDP performance, which is from Torch Titan using the Torch compile, got about 1340 teraflops, which is about 20% slower. So we basically question if it is best. So we did a lot of optimization, and we got finally the green bar here as a motivating number as a 2020 teraflops. So this is the NeMo framework using FSDP, basically the Megatron FSDP. So today, I'm going to talk about what he actually did to actually achieve this number. So let me get to Megatron FSDP. So Megatron FSDP is all about performance. So we did a lot of work, but all these optimization fall in these 3 high-level categories. So we improved the collective communication performance, and basically making the communication low latency and also uses less resources. So basically having all the computation under overlap with the communication uses more resources to make it faster. Secondly, we thought about the more lightweight buffer management between communication and then computation. And lastly, but not least, we also made the memory usage more efficient for which is also contributed to the performance itself. So today, we mainly evaluated our Megatron-FSDP on Llama 3 family, especially Llama 3 4.5 billion, the largest model. But it doesn't mean like it only works for it. We already have it working for the other models, including the MOE, but it's going to show up soon, maybe within a month. And then the data we are going to show are evaluated on NVIDIA B200 and GB200 GPUs at various scales. And then we use FP8 because that is more efficient for FSDP, as we can do the parameter altogether in FP8. So let me first show the sharding structure of FSDP, comparing it to the one of the FSDP2. So both FSDP2 and Megatron-FSDP does the communication by the granularity of a module here. The module is transformer layer to make the communication more efficient for bandwidth utilization. However, their sharding structure is not the same. So the bottom left figure show how FSDP2 does the sharding, and basically it's a per parameter sharding. And this toy example shows that there are 3 parameters, and by different color, and then we shard them into 2 different GPUs. And it basically shard each individual parameter uniformly across 2 different GPUs. But in Megatron-FSDP, we shard the entire parameter within a module with kind of ununiform way. We basically flatten all the parameters in the module and then shard. This is more like how the FSDP1 did, but we chose this option because it's going to be it is more performance efficient. Because if your layout in the communication buffer and then how it is used in the computation is not the same, you have to do additional copy of data between the computation to the communication buffer with the permutation. When we found that it causes extra about 10% end-to-end overhead. So we chose FSDP to make it less overhead, and then this gives a significant performance boost. And the next problem we look at is the repeated collective buffer creation in the communication. And to show it, we have a toy example here in the, as a FSDP routine in the backpropagation. So at each backpropagation, in the transformer layer, you are supposed to gather your parameters, and then the parameters will be used for the computation, and the result of the backpropagation will be basically the gradient supposed to be reduced scattered. And then at every time you call these communication calls, you are supposed to put the data in the temporary buffer. And then how the baseline FSDP does it is basically using the caching allocator, which is literally the torch empty API. Using it is not a problem if you have ample memory left in training, but if your remaining memory is very marginal, then it basically needs to deallocate some of the small tensors and then create the big tensor to actually put the result of the communication. So we found that this causes some overhead, not some overhead, big overhead. So what we did was allocating persistent buffer at the beginning of training. We basically use 2 buffers, so we double buffer it, and then just reuse them across the entire training. So every single communication call, we just reuse one by one, and then the other one, interchangeably. So we remove all the overhead from training for this. So for Llama 3 4.5 billion, we got about 1.5% speed up. But this is the case we have an ample amount of memory left. But if you don't have that much memory left, the performance gain is much bigger than this. The next problem we look at is the collective performance itself. So baseline FSDP communication, like OR-gather, reduce scatter, has a lot of problems. It basically uses about 8 to 32 stream multiprocessors from the computation. So computation kernels are supposed to be much slower while they are overlapped with the communication. And I have 2 GPU traces in here. So both of them are from the Llama 4.5 billion. And then the left side is 4 transformer layer forward, and the right side is the backward. So except for all the, except for those boxes in the red and then purple color, those are communication calls. The rest of them are computation kernels. And as you can see, they are all overlapped, pretty much all overlapped with the communication kernels. So making them slow, since they are losing about many SMs for the communication. And then another problem we see is the extra latency to copy the data between the kernel and the user memory. So this is a repetitive overhead. And then finally, the baseline kernel, baseline communication kernel uses a slow ring algorithm. And this is a hop latency bound. So if your message size is small, or if you're training on a large network domain, then basically your training is going to be more network latency bound. So we use nickel user buffers. So we basically use the capability of nickel to register user-defined CUDA memory, and then we basically avoid any need of copy and make the buffer itself to be self-contained for send and receive and operate. So this enables a zero copy, so we remove all the overhead for the extra copy latency. And then this enables the capability to use more features of NVIDIA NVLink and InfiniBand, such as multicast that needs only 1 to 4 SMs compared to 8 to 32 SMs. And then SHARP that basically offload your reduction operation from GPU to the network switches. So the speed up is shown in this graph. So with the NVLink and then InfiniBand-SHARP with the nickel user buffer registration, we got visible speed up. So we have two data here using 64 B200 GPUs and 64 GB200 GPUs. And then their network topologies, their network structure is different. For B200, the NVLink domain is only 8. So we do NVLink-SHARP in the 8 GPUs. And across the other remaining 8 GPUs, we do InfiniBand-SHARP. For GB200, it has 72 GPUs connected by NVLink, so we just do the NVLink-SHARP. So in both results, both GPUs, we get 5% and 8% speed up, respectively. Right. So let me just speed up a little bit. OK. So the next problem we look at is the need of copying your gradient after your backprop to the communication buffer. I already mentioned at the beginning of this talk that the FSDP2 needs an additional copy of data with the permutation, and that causes about 10% overhead. And that is shown in the small code snippet at the bottom left. So for FSDP module, like a transformer layer, you have to do all, for each parameter in the module, you have to do gradient computation, and then the output gradient is supposed to be hoarded in the temporary buffer, and then finally permuted and copied to the reduction buffer. But Megatron-FSDP, we don't need the permutation, right? But baseline, our baseline implementation still did the copy. So we basically removed the copy by providing the pointer to the reduction buffer directly to the computation. So the computation result can be directly written onto the reduction buffers. So all over is gone, and that was actually 2% extra benefit here. So in Megatron FSDP, so we don't do any extra buffer management in training. So another problem we look at is the large memory need for hiding the FSDP communication. So the model of FSDP is basically hiding all this communication under computation. But this is ideal. Not all time it actually happens. So in reality, you can see what's shown in the bottom left. If your computation volume is not enough, your communication is supposed to be exposed. And this computation volume is proportional to your activation size, such as your sequence length, microbatch size. To actually hide it, you're supposed to increase your microbatch size per GPU or reduce the tensor petal size. So you can make your figure looks more like a right side. However, that needs more GPU memory. So what we explored is offloading the activation stores to the host memory, CPU memory, and then prepatching it back to GPU. This is not a brand new idea. This has been there for a while. But then this was not that popular because the connection between CPU and GPU was very slow via slow PCIe. But now, this is now becoming more realistic with the help of the Grace NVIDIA GPU system that supports up to 900 gigabyte bidirectional chip-to-chip bandwidth. So I have two GPU traces here again. So it looks the same as what I showed before, and then there are two additional information. So the pink color and then the green color are the time, the bubbles taken to offloading your activation to CPU, and then prefetching it from CPU to GPU. So left side is forward propagation, right side is the back propagation. So as you can see, since the bandwidth is much faster, all this offloading and prefetching can be hidden under computation, and there's no impact to the computation under overlap. So in Llama 345 billion training, we were able to offload 76% of the activation to CPU and bring it back to GPU, and then we were able to remove all the unnecessary recomputation, giving about 25% extra speedup. So this is the last problem I want to talk about, and this is about the making the memory efficiency better for hybrid FSDP. So hybrid shared data parallelism is the idea of keeping your communication costs lower in exchange for your extra memory usage. So the top side of in the figure is the baseline FSDP, and it shards your all model states across the entire GPU. So if you have 4 GPU, you shard them across 4 GPUs. But hybrid FSDP shards within a partial domain in the GPU. For example, in this figure, we have 2 GPUs to shard, and between the other 2 GPUs, we replicate. So since we have a fewer number of GPUs for sharding, the communication, such as OR gather and reduce scatter, get much faster. And especially if you are able to limit this sharding domain within your fast intra-node network, it's going to be much faster. So this is well used to train large language model. But the problem is now you have to care about the memory usage. So you have to juggle how big the sharding domain has to be, otherwise you're going to hit the out of memory. So what we basically did was optimizing the hybrid FSDP, doing the full GPU sharding for the optimizer state. So bottom left figure, the top one is what you just saw for hybrid FSDP, and the bottom figure shows what we did. So for compute parameter and then gradient, we do hybrid sharding. But the optimizer state, we do full sharding. So this basically applies the full sharding to 70% or even more of your model states. So this can give you more scalable memory saving at large scale training. But the good thing is that there's no perf loss in doing so. It's just more memory saving, but there's nothing you lose. And compared to the baseline FSDP, let me explain how it works. So the right side of the diagram is the timing diagram for FSDP and hybrid FSDP with our optimization. And the baseline FSDP, we have basically this is the backprop. So we have a backprop computation, and there is a reduced scatter and OR gather happening at the same time, right? And then if your communication takes longer, they are supposed to be exposed. So in our advanced hybrid FSDP, you do the reduced scatter in the sharding domain, because your sharding domain is smaller than your full domain. So, and in our case, we assume that we can remit it within the fast NVLink domain. So it's going to be much faster compared to the baseline reduced scatter. And then after the reduced scatter, you're going to have a smaller message size after the reduction, and they are supposed to be reduced again across the replication domain. Sorry, not replication. I mean across the other remaining domain of the full sharding. So that's why you have another reduced scatter, and that happens after the first reduced scatter. And since they are not overlap in network resources, you can actually overlap with the parameter OR gather in the NVLink domain. So this is how it looks like. So you can make your baseline communications faster, and there's another communication that can be totally overlap with the other communication. So basically, there's a speed up, And then there's also memory saving. So I went through all the techniques we did, and then let me close the performance section by revisiting the performance result that I showed at the beginning. So we basically achieved 2020 teraflops using all the techniques that I talk about today. And then that is about 70% speed up over the best 3D parallel mapping and 50% speed up over our baseline FSDP. Right, that's about the performance section. And then my co-presenter Cory is going to talk about the API details.
All right, I'm going to fly through this. Yeah, so we just talked about how Megatron-FSDP works, and I'm going to talk about how to actually use it. So Megatron-LM's training framework already natively supports Megatron-FSDP, but we also support a fully sharded interface for using models outside of Megatron-LM. So all you have to do is fully shard your model and optimizer, either together or separately, and Megatron-FSDP will schedule your model state behind the scenes. The API does explicitly ask for a few things, such as the device mesh that I'll talk about soon. But specifically, what you want to know is how to set up the FSDP and HSDP sharding strategies. So we have basically these zero redundancy enumerated arguments 0, 1, 2, 3, where you can set if you want to configure sharding for your optimizer, your gradients, or your parameters. And it's for both the inner and outer sharding domains. So the outer sharding domain can either be the sharding domain for optimizer stateful sharding, or it could just be replicate, like in classic HSDP. There's also an argument that's really important where you can configure the module classes that you want to shard and synchronize as shard and communicate as a synchronized group. And this is really interesting. So we call these unit modules, right? But these unit modules, or choosing these unit modules, comes with a lot of nuanced trade-offs. The goal really is to maximize memory utilization while minimizing the amount of nickel calls. And larger communication groups actually reduce the amount of nickel calls, but also increases the memory floor of allocating these layers into memory one by one. So you have to consider how your unit module sizes trade off memory and nickel calls, and also that further affects compute collective overlap, and also the micro batch size that you can fit on your GPUs. And also, speaking of performance, we have a wide variety of performance switches as well. So like you can configure nickel user buffers when you're using Megatron Core. You can choose whether you want to synchronize gradient reduction or outer data parallel communications every single step, or only on optimization steps. And then finally, also basic BF16, FP32 mixed precision options for the optimizer. I'm also going to touch on the device mesh. So Megatron-FSDP's device mesh fully describes its distributed environment, which includes the outer and inner sharding dimensions for data parallelism, context parallelism, and tensor parallelism. We also support expert parallelism using an auxiliary expert data tensor parallel device mesh to support MOE models that we'll be testing with our clients next month. It's an MR. It's like in the CI/CD chain. It's going to be merged really quickly, very soon. But yeah, we went with device mesh because it provides a really intuitive user interface for managing parallelism. And it's also a vehicle for users to integrate their custom distributed environment into Megatron-FSDP seamlessly. And through the scaffold that device mesh provides, we actually support both Megatron and D-tensor-based parallelisms. And you can actually check out some of those recipes in NeMo Auto Model, or just hook up the device mesh that Megatron-FSDP uses with the device mesh that's used in D-tensor-based training frameworks like Torch Titan. I'm going to quickly touch on checkpointing. Pretty simple. Model and optimizer checkpointing are supported. We use Torch distributed checkpoint for saving, and you can also convert distributed checkpoint into either unsharded Torch save, or even further into Hugging Face safe tensors for sharing with other people. And finally, you can load Torch save checkpoints before fully sharding, or load Torch DCP checkpoints after fully sharding. So there's a lot of flexibility when managing your pre-trained state. And yeah, just to wrap things up, Megatron-FSDP installation is really simple. You just pip install Megatron-FSDP from PyPy. If you're already using Megatron-LM, you don't need to do anything because it's already, FSDP is already a submodule of Megatron Core. Megatron-FSDP is thoroughly integrated into the PyTorch and NVIDIA ecosystem. So we support both compute in both BF16 and also TransformerEngine current scaling, delayed scaling FP8. While MX FP8 and FP8 weight support will be promptly tested and supported in early 2026. Day 0 support for Megatron-FSDP is in Megatron-LM, Megatron Bridge, NeMo Auto Model and BioNeMo recipes. And I've also casually tested Megatron-FSDP in Torch Time, the Hugging Face ecosystem, Lightning, and native PyTorch. So it's generally compatible with most training frameworks. Yeah, and we definitely encourage open source contributions. So whenever you guys find a bug or want to give us feedback, just open issues or PRs into Megatron LM. And just keep in mind that we're still in the alpha and beta stage of Megatron FSDP. So definitely expect some bugs or friction. Before I end this, I'm going to skip through the appendix slides. I just want to mention that NVIDIA has a lot of events this week at Open Source AI Week, so don't miss it. There's a QR code that I'm going to leave on the screen for as much as I can. And then also Nemotron, which is an open model, open data, open libraries, and finally also open research. You can check out all of NVIDIA's open source libraries and that QR code. And I'll open the floor to questions. Okay. I think this guy raised his hand right here. Yeah. Yeah, just speak up. Yeah.
So, how many of these optimizers do you think would carry over the FSDP? Right? For example, activation offloading comes from, let's say, GB200. Activation offloading comes from GB200. SHARP basically comes from like the switch infrastructure, I guess. And the variable sharding that you set up for parameters or optimize the state, I'm assuming is just as much work to like set up the detensors as well. So if we just did the work, like how much of that gap will Torch Titan bridge, do you think? Obviously, we can't do the flat parameters, for instance, because that's pretty significantly breaking for Torch Titan. But how much do you think will carry over?
Okay.
A great talk, by the way. Thank you.
That's great. No. So the question is, can we upstream any of these features to FSDP2? The answer is we're definitely willing. This is mostly our research code, to be clear. So we kind of wanted to mess around with a bunch of different optimizations, and that's what Megatron FSDP ended up being. But we're definitely open and willing to reach out to the FSDP2 team to upstream some of these features. I think to answer your question, the fully sharded optimizer state, that seems like a potential opportunity to upstream because it's literally just establishing a view into a fully sharded view of the model parameters and also the gradients as well. So it adds an extra all gather, extra reduce scatter only on the before and after the optimizer step. So that can be upstreamed. As for the other stuff, definitely can be much harder because we have our own strided sharding configuration. We have our own uneven detensor kind of management for dealing with flat buffers, since we don't actually split every parameter evenly like FSDP2 does. But no, like good question. Like there's a lot of debate to be had. I think in my mind the optimizer sharding would be the easiest. Maybe one more question, or yeah.
Hey, really nice talk. I just had a quick question. You had to do a lot of optimization in order to get this over the line, right? So I wanted to just get an idea, like how much of those individual optimization contribute to that performance? For example, mainly I would like to understand like how is the SHARP, especially from InfiniBand-SHARP, how is that contributing? How much does it contribute to the performance improvement?
Right. Yeah. Basically, in each slide, I put some number, like how much they contributed. But you know, if you want to make the full stack bar, I probably we need to like rebuild the whole thing, like because we, you know, basically that improvement happens in different configurations. So you know, to actually get the full stack bar, we need to probably just look again. Yeah.
Okay. Thank you.
But then we already have some numbers, so you can probe that for how much they contribute.
Sure. Thank you.
One more question.
What's the detensor placement you invented in order to represent the flattening?
Yeah, so Jack would be a great person to answer this, but the idea is simply just we write in Torch GCP metadata so that when we write out the uneven detensor data, we write it correctly, unevenly to shards. But basically what you need to know is like, with uneven detensors, like the quirks are, you'll sometimes get empty tensors in your detensor.local tensor. So that's something you have to take care of. And when you're all gathering, right? So you want to make sure if you find an empty tensor, just either concatenate it, or like if there's no empty tensor, if there's no tensor at all, you just have to ignore it and concat whatever ranks actually have those tensors. But yeah, we have all these utilities. It's basically all baked into pip install Megatron FSDP. And if you want to all gather these uneven parameters into one unsharded parameter, we have utilities for that. So it's complicated, but we have the API. Great question.